Thank you very much. So first, thank you for the invitation to come and give a talk. It's a pleasure to be back in Les Houches after a long period without possibility to be live at a conference. So first, let me introduce myself. As you see, my name is Thierry Jamarchi. I'm working at the University of Geneva. Not very far from here. It's essentially 1 hour from here. And it's nice to enjoy the beautiful sunshine of Les Houches today. Okay, more seriously, don't hesitate to let me know if you cannot understand me. The mask is not helping communication, so don't hesitate to shout or say something if I'm mumbling in my beard. And the second thing, don't hesitate to interrupt me constantly during the lectures. Ask questions. This lecture is yours, and I would say the first lecture will be also to determine a little bit what you know, what you don't know, to position the two other lectures, because for me it's very difficult to decide what to put in this lecture. I've been ordered by our bosses here to talk about quantum transport, which is a topic that I like very much, so there was no problem in doing this. But this is a subject on which we could spend 6 months. So I had to make choices. So today I've chosen to do something extremely simple, just to go with very simple notions that you probably all know. Just to know as a poll, just as a free poll, who has seen something called the Kubo Formula? Okay, so I'll do the Kubo Formula today, so don't worry. For those who have not seen it. Voilà. So if you think I'm going too fast, shout. If you think I'm going too slow, shout. Don't hesitate. In general, if you don't say anything, I have a tendency to accelerate. So if you don't intervene, the lecture will become faster and faster. So don't hesitate to slow it down. I've also, in principle, the idea would be to do 1 hour and 15 minutes of lecture and then keep 15 minutes for questions at the end. But again, don't wait till the end. If you have one question, ask it at the moment where you have the question, and don't wait till the end. Okay, the idea, but we'll see if it works that way. Today, simple notions on transport, practically telling you a nice story, showing you very few experiments. I will show you more tomorrow in various systems, but we'll see some of them today. And tomorrow, to do more the effect of interactions on transport. You heard about Mott insulators in optical lattices, and okay, let's try to connect this. And in the last lecture, depending on what we did during the 2 first lectures, perhaps we will have time to cover a little bit Hall conductivity and disorder effects, something which is dear to the 2 people in the front row here. But we'll see. If we don't have time to do disorder, no problem, we'll do something else. I will try to write, not on the board, but to write on the tablet. That way I can give you the PDF of the notes after the thing. Same thing, if it's not if you cannot read it, don't hesitate to say it. I try to write bigger or something like this. Okay, so I'll use the slides, of course, mostly to show experimental data and try to go between the slides and the thing. So let's maybe before we go more, I'll go with this. And so let's start with quantum transport. Just to see if you can see what I'm writing, if it's legible. Okay, and the first thing we will do is, of course, basics of transport. And same thing, the first question that you would ask yourself is why look at transport? So first, why look at transport. So you all played, I guess, at some time in your studies, whether you do cold atoms or you don't do cold atoms, you all played with the device, which is a battery, which you connect to a certain system here, a lamp or whatever. And then you have measured typically, so you have something which is at a voltage V, and you measure the current I, which is going through your system. And then you play and determine typically the function I of V or V of I, and very often you found it's linear, but not always. And the reason usually why you want to do this thing is because it gives you informations on what is your system, what is inside your system. So you get information on the properties of the system. And that's a very simple thing to do, but actually you have to be careful, because actually it looks simple, but actually it's quite complicated. Because your system is out of equilibrium. So actually transport is the simplest out of equilibrium experiment that you can do. And if you were passing, of course, 1 microvolt through the system, you're happy with looking at the linear response, saying that the voltage is proportional to the current. If you take the same system and you put 2 gigavolts on it, most likely it will not follow a linear curve. So actually, technically, you should worry about dealing with all the aspects of out of equilibrium physics. And if you think about it, it's very, very nasty to do out of equilibrium physics, because you throw away all the tools that you have, which you use when you are in equilibrium. Forget the Boltzmann distribution. Forget the fact that the system is at a given temperature. You're injecting energy in the system, so this energy will evolve with time. You know, all the notion of looking at the stationary state of a system are disappearing if you're really out of equilibrium. You need to work harder to make them work. So all questions that when you do transport that I will essentially ignore during this lecture is the questions of where the dissipation can come from, where what happens if you have isolated systems versus systems which are in equilibrium with a bath. If you do condensed matter, very often your system, the electron gas, for example, is in equilibrium with the vibrations of the lattice. So you can evacuate energy by making the lattice vibrate. In a cold atomic system, you realize that this will not be the case, for example. But you have other mechanisms that could dissipate energy, losses, and so on and so forth, that you might have to worry about. So I just want to mention that this is a super complicated problem, actually. If you want to put a little bulb in contact with a battery. Actually, of course, when it's complicated, people cheat. And the way to cheat, which we will do during this lecture, is to say, let's look at linear response. So most of the transport which is done in linear response. So you assume that you put a small voltage, and then you get a small current. And of course, then you can sort of approximate the relation between the current and the voltage by saying that, for example, the current is proportional to the voltage with a constant that you will call here the conductance of the system. And then because you do linear response, usually it's much simpler, and we'll come back to this, to compute G. Why? Because as usual, it means you push the system just a little bit out of equilibrium, which means you can compute G by looking at a system which is in equilibrium. So this is a cheat that people have used. Okay, I just want, before showing some slides with some experiments, I just want to, by hand, show you various transport quantity. And some, of course, basic vocabulary, let's say. And then I'll show you real stuff, because otherwise it's really too esoteric. But I assume that every one of you has at least one time measured the resistance of something during your bachelor, and that you had to suffer through this. Okay, so how do you modelize? Okay, maybe actually I will do the opposite. Let me go back to the show here, and let's go. So, okay, in condensed matter, this is the bread and butter of every laboratory. Yeah? You don't have a lab which is not measuring the resistivity. I'm going away out of the camera, so I shouldn't move. Okay, I'm stuck here. That's. So this is really the typical transport experiment where you have the battery, you connect a bulb, and then you want to compute the current voltage characteristics. That's what I just said before. Now, how do you modelize these things? Well, you say I have one reservoir of particles, which is here, which can inject particles in my system. So my bulb here would be the white stuff. And then I have another reservoir of particles, which is here, which gets the particle which have gone through the system. The battery contains both, essentially, this reservoir and this reservoir. Okay. And it sounds innocent to tell you that you will modelize the system like this, but as you will see, this allows to do pretty interesting calculations. Now, you're not always in a situation like this. And let me show you another situation which is quite interesting. This is what people call the scanning tunneling microscope, which is the STM, where you have a metallic tip that you bring close to the surface of a material, and you want to have electrons which will go by tunnel effect from the tunneling tip here inside the material. So in a way, you could say that one of the reservoirs is the tunneling tip. The other reservoir is actually the material itself, and the system is the vacuum. There is nothing here. You just try to pass particles through the vacuum. Now, here, very often, the curves are absolutely non-linear. You cannot write something which is a linear relation between current and voltage, and so one has to worry about this non-linearity. There are other out of equilibrium situations that I will not discuss. I just want to mention this just to say forget about them. But you can also view them as transport situation. For example, imagine that you have a bath of particles, which I would call the blue particles, and then you create at time zero a red particle. For example, you flip the spin or the isospin of the particle. And then you want to know, after a while, where the red particle has gone. So you want to follow the trajectory of the red particle, and you can view this as a kind of transport experiment where you visualize this red particle as being alone, but in contact with a bath of excitations, which is provided by the blue particle. So this is very interesting and can be done very well with cold atoms. There are experiments, for example, in Florence with rubidium potassium mixtures. But I will not mention it. So here is the experiment which was done with potassium atoms, which are kept in place initially and then released inside the system. This is another experiment which was done in the group of Emmanuel Bloch, where you change one isospin, so you get the red particle as a certain spin, and then you prepare each line here is a red particle which was put at the center, blue particle that you don't see in this imaging system, and then you release, you let go, and after a while you try to see where the red particle has gone. You can view it as a transport experiment, you can view it as a random walk, a quantum random walk, and so on. These are very interesting situations, but I will not discuss them. Let me show you an example of what I just showed before. Let's go back to the transport, which is the modelization of reservoir 1, system, reservoir 2, which is a little variant on the scanning tunneling microscope. So this is normal material. You know it very well. This is unknown material, and by looking at the transport between the two, you want to understand the properties of this unknown material. Okay. You can do something a little bit different. Let me skip this. Here, just to show you something, because you will see the equivalent in cold atoms a little bit later. This is what people call quantum point contact. So I'll explain to you how it's done. You take a plastic film, you coat it with metal, actually aluminum, which then, by lowering the temperature, you can make superconductors. So these islands here are superconducting. And then you push below the system, which deforms and cracks. And so reservoir 1 is here. System is the vacuum between the two. And reservoir 2 is here. The trick is that you can now have superconducting islands here. So systems in which interactions will play a role. Not free electrons or not free particles, but attractive interactions here. And one question would be, how does this attractive interaction modify the transport? So would you like to take a bet? What do you think the current voltage characteristics? So now the voltage is the difference of voltage between the two reservoirs here. And the current you can measure by counting, looking at how many particles are going on, how many electrons, so you measure the current, is going from one side to the next. So let's take a bet, just a bet. First, if the material here were free particles, no interactions, what do you think would be the current voltage characteristics? You have two systems and a tunnel effect at one point. Now I put a voltage, this will create a current. What is the current as a function of the voltage? Exponential, why not? Other proposals? Steps, okay. So you see, transport is not so easy. We already have two theories in the room. Okay, so we'll keep a little bit for later the case of the normal system. I'll show you the curve for the superconducting system. Here it is. Several curves here, which corresponds to pushing more or less on the road, which means the barrier is larger or smaller. This is the worst barrier. This is very small tunneling amplitude. This is practically no crack between the two systems. You see, it's a very nonlinear current. So this is the voltage, this is the current, and they are normalized to the gap, the superconducting gap of the material. Okay? And you see that this current voltage characteristics is highly nonlinear. So linear approximation that we will discuss later. Okay, we can discuss how good it is. It has even weird shape here. You see it does blip, 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 and so on. and gets progressively smoother as the tunneling is getting better. You see also that if you go at voltage which are very large compared to the gap of the superconductor, the characteristic current voltage is essentially linear. So maybe not all hope is lost for getting a linear response. So if the gap was 0, to spoil the fun, you would get a linear current voltage characteristics. Now, what is the slope is another story. But the current voltage characteristics would be linear, and we'll come back to that. So this is one example of transport which is done between two superconducting materials, two superconducting big reservoirs, and trying to pass the current through such a system. Okay? So let me go back, interrupt a little bit the presentation, and try to summarize a little bit what we discussed here on the notes. So again, we have our situation here with a battery and our little system here. And usually, but not necessarily, people can look at the steady state, which means you establish the voltage, and then the current is doing weird things, which could be super interesting. Like it goes up, then it does strange things, but then you hope that it will reach a steady state in which you measure the current voltage characteristic. It's not obvious because that you will reach a steady state, because again, it depends whether you can dissipate the energy that you're injecting in the system, and we'll come back to that a little bit later. Again, modelization, which is to say that you have reservoir, then you have your system here, and then you have, again, a big reservoir. Voilà. I just want to establish a vocabulary, and I'm sure most of you know this vocabulary. So if I say I have a voltage difference between the two reservoirs, so I expect that I will have V, the voltage, which is the resistance of the system times the current. So this is the resistance. Or I could say that I is equal to G times V, where this is the conductance. And now the problem is that clearly this quantity, which is the conductance, a priori depends on the size of the system. So naively, if I have a system which has a certain, whoops, thank you, Microsoft. If I have a system which has a priori a certain size and has a certain resistance, now what will happen if I put now a system which has twice the size? Naively. Yeah, naively you get double the resistance. Not always, spoiler alert, if you have disorder, especially in 1D, it can be much worse. But let's ignore that for the moment. The idea would be that you have Ohm's law. If you put resistance in series, they add. So the resistance is actually proportional to the size L of the system. So you like to define a quantity which is independent of the size, and this is what people call the resistivity. So I will introduce the resistivity by saying that the resistance is equal to the resistivity of the system times the size of the system. Okay? And in the same way, you can introduce a conductivity, Vt, sorry. I told you that today would be simple. Well, it will be a little bit less simple in a moment, but conductivity, which is sigma, and it's usually 1 over rho. And of course, it measures, if you want, the capacity of your system locally to diffuse the current, to have something which is not a perfect conductor. Okay? I let you do as an exercise to show that in general, Ohm's law means that the resistance of the system is the resistivity times the typical dimensions of the system to the power 2 minus d, where d is the dimension of space of the system. So what we did was d equal 1, a system in one dimension. Now think about a cube of typical dimension L, and what is the resistance of such a cube? This would be d equal 3. Think of a square and imagine the resistance of a square. What happens if you grow all the dimensions of the square? But again, you put a voltage. Let's say you have a system like this. You put a voltage here, here, and you pass the current in between. I'm sorry about this. So the current, the total current which is passing is, of course, the current which is passing through the whole system. So I let you do as an exercise. If tomorrow you have not done it, we can do it together. You see that d equal 2 is a special dimension, clearly, because the resistance is equal to the resistivity. Okay. So this is one type of transport that we discussed. I should have called them A. These are the transport that correspond to the one we saw. B, we have the quantum point contact that we already discussed. In which you would say, I have my system, and then there is one point in which by tunneling I can go to the other system. You know second quantization. You learned it for some of you perhaps last week, for some of you before. How would I represent the tunneling here? Well, I would write an Hamiltonian, which is saying I have a certain amplitude, let me call it tau. And then what I do, I destroy, let's call the particles here C, the particle here D. I would destroy a particle C at x equals 0 in the system. Let's call the coordinate, let's say at x equals 0. And I will recreate a particle D at a certain coordinate in its reservoir, x1, doesn't matter what is the coordinate, or let's call this one x2 if you prefer. So this is the point at which you destroy the particle. And of course, if I was just doing this, the Hamiltonian would not be Hermitian, so I need to add the Hermitian conjugate, the x1 here. So this is the coordinate which I called x2, and this is the coordinate I call this x1. And of course, if I want the full Hamiltonian, I have to write the Hamiltonian of the left reservoir plus the Hamiltonian of the right reservoir plus this tunneling Hamiltonian. Okay. As I said, you saw two examples. One was this superconducting material. The other was the STM. Both situations are described by this kind of quantum point contact. And again, note IV not necessarily linear. Okay. Do you know other transport quantities or situations? Yes? Momentum. You could measure the momentum, yes. How the momentum is transported. Another quantity. Matter, which is what we did here, essentially. Sorry, heat. Voilà. Another thing you can measure, you said momentum. It's perfectly okay. You could measure how the momentum is transported. You could measure other quantities, and one which is very natural is the energy. How do you transport energy from one reservoir to another, so heat, for example. And then you can play with a lot of ways to imbalance your system. Because you could put a voltage and ask yourself, how is heat transported from one reservoir to the next? But you could also put a difference in temperature and ask yourself, how is heat transported to the system? You could also ask, I put a difference in temperature, how is charge transported? So there are plenty of transport quantities, and we, of course, will not cover them all in the lecture. But I want just to mention one. So again, heat. I put momentum also, why not? Momentum, so on. One that I want to mention is spin. Because certainly in condensed matter, electron has a spin 1/2. And so in cold atoms, it's a little bit more complicated. I know that you know all about SUN now, and you know that the fact that some atoms have a very complicated structure. But let's keep it simple. Let's assume that we have particles which have just another degree of freedom than the charge, which is the spin. You can do the same thing. You could say, for example, let me consider that I have my two reservoirs, my system here, which is whatever it is, and then I imbalance the system not by putting a voltage which will affect in the same way the spin up and the spin down, but I will put a magnetic field. The magnetic field will make it, this is for electrons, in cold atoms this will be something different. You will imbalance the population of n up and n down. And what you want to know is what is the spin current. And the spin current is the current of spin up minus the current of spin down. So this is a quantity which is relatively natural to measure, of course, in condensed matter, because as I said, electrons have a spin 1/2 and you want to measure it. And so people in cold atoms, I will show you how they devise tricks to measure these kind of things. Let me ask you a question. What would happen on the spin transport if I was, for example, let's be simple. I have only spin up here and I have only spin down here. Of course, it's not a situation that will want to stay. The spin will want to diffuse, and the spin down will want to go to this reservoir. The spin up will want to go to this reservoir. And after a while, you will equilibrate the population of the two species. But imagine I put a superconductor here. What will happen? In a superconductor, the spin up and spin down are paired, which means you cannot have the spin up go that way and the spin down go the other way. So the superconductor for the spin will act as an insulator. It will not prevent the charge current to go, because that's perfect. You move the pair and it goes very well in a superconductor. But it will prevent the spin to go. So depending on the properties of your system, you can analyze these properties by looking at various transport coefficients. And again, we will not cover everything, but I just want to mention it. And finally, one which I like, so I cannot, is the Hall effect. And I mention it for two reasons. The one is because it's super important. The second, you will hear in the talk by Monica a lot of things on topology and artificial gauge fields and way to realize the equivalent of a magnetic field in cold atomic systems. And the Hall effect is one of the sort of most ancient manifestations of this. So I don't know if you have memories of, I would say, your early days, but the whole effect is that you take a system and then you put it in a magnetic field. Again, 4 electrons, something that will produce a Lorentz force. So then you try to pass a current here in this direction, but of course the particle will be deviated and they will go and accumulate on the top of the system. They cannot exit, so after a while you will have an electric field that will be created by the excess of charged particle here, the depletion of charged particle here, and this electric field will exactly compensate the Lorentz force. So actually you have here an electric field which will act, which means you have a difference of voltage here, which people call the Hall voltage. And this electric field compensates the Lorentz force. So you can write an equation which is Q times E, let's call it EY, is equal to the Lorentz force, which is Q times the velocity of the particle vectorial, the magnetic field, and the current is the density of particles times the velocity. So you can also rewrite this as Q times the current times the magnetic field divided by the density of particles. And you immediately see from this little argument that the electric field in the Y direction is proportional to 1 over the density of particles. So this is a very simple thing that people have measured for ages, that condensed matter people like because they say that it gives them the density of carrier in their solid, which they don't know, and which is almost always wrong. So this is, and this gets wrong for many, many reasons, and we'll examine some of these reasons perhaps in the third lecture. One of the reasons is that indeed you can relate this quantity to topological properties of the material, and this continuous function here, which is 1 over the number of carrier, is strongly affected when the magnetic field gets large. And finally, I want to mention a last transport property. I'm sorry, this is a little bit like a catalogue à la Prévert, which is the fact that you're not obliged to measure transport by response to a uniform and steady state voltage, but you can also make the voltage oscillate, and then you will measure finite frequency. Transport. Okay. So this is something that people like to do. You measure J of t, which is the linear response, for example, let's call it sigma of t minus t prime to an electric field that you have put at time t prime. And of course, if you go to Fourier space, this convolution product is just telling you that J of omega is the Fourier transform of this quantity here at the frequency omega times the electric field at frequency omega. So if you apply an electric field at frequency omega, you can expect a current at frequency omega, and the proportionality constant is what you would call the conductivity at the frequency omega. And actually, in condensed matter, it's not so easy to measure. It's not so easy to measure because, of course, if you measure at very low frequencies, you just put an oscillatory signal on your voltage. But actually, to get interesting things, you need to go to gigahertz, and then the only way is to shine light on the material and then measure what is reflected, which will tell you essentially how much could be absorbed by the material, and then that's the way you access to this quantity. But I won't go too much into details in this because I'll show you the cold atom version. Okay, so we saw a lot of transport now. What about cold atoms? You know, cold atoms can do everything, so let's measure transport. And actually, it's super complicated. That's the technical term, the very, very... Why is it super complicated? Well, because actually, if you think about it, you have a little ball of something which is trapped, and that's it. So what you want to do is to do transport on a little ball of gas, which can be with optical lattice, without optical lattice, and whatever, which is there in a box or in a parabolic trap. I hate parabolic traps, but that's another story. Can be in a box. Let's do a box, much better. And now, how would you measure transport? What would you do to measure transport? Sorry? If you are with this, you cannot do much indeed. So what people did, they did a kick. They kick the system. So that's, let's say, the first method. You can kick the system. By moving, let's say, the center of mass of the trap or of the box. But you see that now it's a nightmare because things will start to get in motion, but then they will hit the wall, bounce on the wall, cancel part of the current which is going in this direction. So either you have to measure very fast, and then you're not sure you've reached a steady state, for example, or you have to worry about the bouncing on the walls, the fact that you have a lot of problems. So the kick has been used and has been used with success. I will perhaps show you some measurements on the third lecture, but it's a complicated business to really measure things with a kick. Another thing that you can do is actually shaking. And that I will not detail too much today because I would like to come back a little bit later. But imagine you have your system in an optical lattice. And you have, let's say, particles which are sitting, particles which are sitting at the bottom of the optical lattice. Let's say I put one particle per site. What you could imagine doing is say, can I change, for example, the amplitude of this optical lattice? And that, I'm sure you will hear a lot on this in the talk by Monica. It's not the same thing if you shake very fast, which is what she will mostly tell you, or if you shake slowly, because then you could imagine that this is a little bit like applying an electric field and you're measuring some finite frequency conductivity. And actually, the first people to do this is the group of Tillman Esslinger in Zurich. And so this is in a paper. So you sort of change the amplitude. So this is the amplitude shaking. And this is Stofferle et al. And this is PRL 92 130 403. And this is already ancient. This is in 2004. And you definitely, when you do this, you provoke excitations in the system. And in particular, you can take one particle on one side, it's gone on the other, and so on. And I keep a long story short, you do not measure the conductivity. So this does not measure. But it's related. And actually, you can do better. And this is something we propose with Akiyuki Tokuno a little bit later. This was PRL 106, 205, 301. This was 2011. Is not to do an amplitude shaking, but to do a phase shaking, which is to change not the amplitude, but to move the maxima of the potential in phase. So you take the optical lattice and you do this. or you keep the optical lattice stable and you take the trap and you do this. And if you do this, you can show that you measure the finite frequency conductivity. So this is a good way to measure the finite frequency conductivity. But difficult with this method to do the steady state measurement. What you would really like to do is to have one reservoir, the system, and the other reservoir. Okay, let's see. So let me move forward. Oh, yeah. I just wanted to show you examples. This is not super. These are other examples of transport. So, for example, here is on some organic conductors, which are, if you want, these are like tubes that you could have where the electrons essentially move in one direction. Here is what the frequency-dependent conductivity would look like. You have, as a function of the frequency here, you measure the conductivity of the material. You see that it has a certain curve here. And now we go back to the idea that this gives you access to some physics of the material, because actually when you plot this as a power law, well, you get a very nice power law, and this is an indication that these materials obey a theory, which is the theory of interacting 1D electrons, which people call the Tomonaga-Luttinger liquid. And this is a way to characterize that this system have this property. So I don't want to go in detail, just to show you an example of measurement of optical conductivity. Just to show you that measuring transport is not easy. Here is on the same material, which again is made of nicely coupled chains. Measurements of the Hall effect. Sounds simple enough to measure the Hall effect. Here is a measurement by group 1, temperature, Hall resistance, which is the transverse voltage divided by magnetic field divided by current. You see that you see a very clear power law dependence, or very clear strong dependence here in temperature, and then going back to another value. Same measurement done by group 2. All very respectable group, excellent groups, not at all amateurs. Here you see no particular temperature dependence here of the Hall effect before it goes back to the same value here. Up to today, the controversy has not been resolved. And as I said, these are good groups who did these measurements. So perhaps cold atoms. Yeah, so I anticipate a little bit on what I wanted to say, but since I showed the picture. So before I show you the cold atoms, today in the remaining time, so we will not do both of them today, but we'll finish tomorrow, we'll see two simple methods to compute transport, which are generic methods, which means they can be used for any system. Of course, it doesn't mean you don't have to do the calculation, and in general, doing the calculation is super difficult, but these are the two methods we will see. One is the so-called Kubo formula. So here is Mr. Ryogo Kubo, who invented this formula in 1957. And practically at the same time, so this is a vision which is very much linear response, condensed matter, perturbation, response, and whatever. You will see what I mean when I say this. And then there is another vision, which was by this guy here, whose name is Landauer, Rolf Landauer, and which was perfected by Marcus Büttiker later, and which is now known as the Landauer-Büttiker formula. But it was also invented in 1957, which is more to see transport as transmission of waves. And this is an extremely fruitful approach that we will do. And these two approaches are absolutely complementary. And by the way, they don't give apparently the same result. So that will be the occasion of a little exercise on why they don't give the same result. So, but before we do this, let me show you the cold atoms. So here is the solution that was brought by Jean-Philippe Brantu and Tillman Esslinger on how to do transport with cold atoms. And this is exactly what you were mentioning. You do a big reservoir on the left, you do a big reservoir on the right, and then you pinch the system here, and this is your system. And depending on how you pinch, the system can be a 1D tube, can be a 2D plane, or could be a big fat tube between the two systems. And here is a more correct view of this. So you get essentially one part on the left, which is big, one part on the right, which is big, and then in the middle, you have the part that you want to study. And then you imbalance these two objects by whatever you want to imbalance them with. You can put a different number of particles here and here, in which case you will measure charge transport. You can put a different temperature here and here, in which case you will measure whatever, charge transport if you want, energy transport if you want, and so on and so forth. You can put a different magnetic field or spin population in this left reservoir and right reservoir, and then you will measure the spin transport, and so on and so forth. So here is the first experiment. So this is literally the realization of the battery, which is coupled to a bulb, even closer to the battery that maybe they wanted, because actually, of course, the difference of population between the reservoirs is not that big, which means your battery is discharging. So you're not exactly in steady state because you cannot provide for a long voltage imbalance, but long enough that you can do measurements. So here is the first measurement that was done on this system, and this is a measurement of the population imbalance between the reservoirs. Population imbalance means difference of chemical potentials, which is the equivalent for neutral atoms of voltage. So this is the voltage difference between the two. And this is the current here. How do they measure the current? What is the method to measure the current? Yes?
Measure the number of atoms over time.
Exactly. You focus on one of the reservoirs and you measure n of t. And dn of t dt, the variation of the number of atoms with the time, is the current. This assumes that you're able to measure the variation of atoms as a function of time with enough accuracy to be able to essentially differentiate this curve. Otherwise, your currents will have huge error bars. Keep in mind, something which doesn't make things simple is that measurements are usually destructive, which means actually this point and this point are not measured on exactly the same system. The system has had to be regenerated, so it might have not exactly the same number of total atoms and so on and so forth, which of course you have to keep well under control to keep the error bars under control. So it's still not simple to do, highly not simple to do. But essentially by measuring here a curve which is the total number of atoms as a function of time on the left reservoir, say, then by looking at this curve, you can get the current. And then for each point on this curve, you can get the current as a function of the number of atoms. So this allows you to get the full IV characteristics, the full current voltage characteristics. So I let you do as an exercise the fact that if you have a constant resistance, then the curve will be a simple exponential as a function of time. You all studied the resistance and the capacitor, so I don't think it should be a very difficult exercise to do. So what they measured here is essentially Ohm's law, but Ohm's law in a very strange situation because actually the two reservoirs are separated by a barrier. So we are talking about the quantum point contact. So it's not that there is a dissipative medium in between or whatever. There is nothing in between. Well, actually, there is something, but I'm cheating shamelessly. Okay. Let me show you another measurement done later, and then we'll go back on this one tomorrow extensively. The main difference is now there is a little 1D channel here. This is, of course, the artistic view, but there is a little 1D channel in between. And now, here is the conductance. So it means the curve, the relation between current and voltage is linear. And now you take this coefficient of proportionality and you plot it as a function of what they call the gate potential, which is the chemical potential of the little channel here in between. And what you see is something which is 0. So the coefficient of proportionality is linear, is 0. Then it jumps to 1. Then it jumps to 2. Then it does whatever it wants. But essentially, it doesn't sort of go smoothly as a function of the gate potential. Beware, and it's not the same graph. Here it's the current as a function of the voltage. So the slope is the conductance. And now this is this slope, which is plotted as a function of the chemical potential of the little 1D tube, which is in between. So this shows that there is quantization of the conductance here in this system. And why it's so, that's something we'll discuss tomorrow after we've seen the Landauer-Büttiker formula, because this allows to understand this. Okay, I think I will stop to show you experimental curves. And we'll start today. I still want to stop at in 10 minutes so that we have time for questions. But I want to start with showing you the Kubo formula, and actually more reminding you about something you probably all know or have seen at some point in your life, which is linear response in general in quantum mechanics. So how many of you had or have well in mind linear response in quantum mechanics? Okay, it's more than Kubo formula. So, yeah. Okay, so let's do this, and then I'll stop in 10 minutes, and we'll continue tomorrow with the Landauer-Büttiker formula, and we'll try to explain this curve out of the Landauer-Büttiker formula. Okay, there are other experiments which are more complicated to explain, which I will show you tomorrow, but for the moment, let's do it. Okay, so this is section 2, which is too important, let's say, derivations. And the first one is the so-called Kubo. This is annoying. Chuck. First one is the so-called Kubo formula. So the Kubo formula, it's really the workhorse of computing transport. But before I do this one, let me just remind you linear response. And if you want to have this derived, any book on statistical physics or quantum mechanics will do. One book in which I find this relatively well done is the book by Mahan, which is called Many Particle Physics. So just one of the many books where you can find it if you want to see this derivation. So this is G.D. Mahan, Many Particle Physics. But any book will do. So what is the idea? You start with an Hamiltonian, which is H0 plus a perturbation. So H0 is not free particles or whatever. H0 is anything. You choose, you pick, okay? And then you add a perturbation here, which I will write that way to keep it general, can potentially depend on space or any other quantum number. And then you have a classical field, which is a number, if you want, which depends potentially on space and time. And that's what you drive your system with. You apply an electric field, you apply a magnetic field, you apply a chemical potential, you apply whatever. You control it from the outside. This is your classical field. And then these fields couple to an operator, O, which is, I will not put the hat because I will keep it for Heisenberg. but this is an operator, and then this operator is potentially a function of space or whatever other quantum number you want to have in your problem. So this is an operator, and this is a number. Okay. So this is, as I said, you apply pressure, you apply a magnetic field, you apply an electric field, and so on. And now what you want to do, you want to measure the average of another operator, which also potentially depends on space, and you want to measure it at time t. So what does it mean? It means that what you want is 1 over the partition function of the system times the trace of the density matrix of the system at time t times the operator, which is potentially a function of x. The density matrix at time t you determine because you know the Hamiltonian at all times, and let's say you know at time minus infinity what was the density matrix of your system. So the implicit assumption that one will do here is the fact that at time minus infinity, the density matrix, rho of t equal minus infinity, is just the thermal density matrix for the Hamiltonian H0. You didn't yet apply the perturbation. Okay, so this is proportional to exponential of minus beta times H0, and the perturbation is applied adiabatically from time. So if you want, I can write lambda of x and t, which is what I want, but I need to multiply by exponential of delta t, where this is 0 plus. So to ensure that when t is minus infinity, this factor is 0. But this is super small, so it will not modify at any finite time what is the perturbation that I'm applying at a given time t. So this is just to ensure that the perturbation dies at time minus infinity. Okay? Of course, lambda of t should not grow exponentially at time minus infinity, otherwise you're in big trouble with this formula. But let's say lambda of t is sinusoidal, for example. So you ensure that it dies at time equal minus infinity. Okay. Let's simplify ourselves. It's very easy to correct if it's not the case. You will take that the average of A of x taken with the Hamiltonian H0, so if there is no perturbation, we'll assume that this average is 0. If it's not 0, you just subtract the average from the operator, and that doesn't change anything. Now, if I want the average A of x and t, and I assume the perturbation is small, whatever it is, I can expand it in powers of the perturbation. So I will have that the average A of x at time t with the Hamiltonian H0 plus whatever lambda O is equal to the average of A of x at time t, but just for the Hamiltonian H0. But this is 0. I assume that this is 0. And then I will have a term of order 1, which has to be proportional to lambda. But of course, at all values of x and t, plus terms which will be of order lambda square. And the most general term that I can write is some coefficient chi of x, x prime, t, t prime, and then I integrate over x prime and t prime. That's just expressing that if I do an expansion in powers of lambda, this is the most general term of order 1 that I can write. Imagine lambda as a kind of big vector. I multiply by a matrix of coefficient, and this gives me the big vector, which is here as a function of time. Okay? If I have something which is invariant by translation in space and time, chi depends only on the difference chi of x minus x prime, t minus t prime. Okay? In Fourier space, so if I do the Fourier transform, So for example, just say a q omega is equal to the integral sum of dx dt exponential of I omega t minus qx a of x at time t. Let's assume that I have something which is invariant by translation in space and time. Then it's easy to check that a of q and omega is the Fourier transform of the function chi of x minus x prime t minus t prime. So it's chi of q and omega times lambda of q and omega. So Fourier mode by Fourier mode, I have a proportionality between the perturbation and the response of the system. So this is perturbation. And this is the response. And the two are proportional. I've thrown away the higher order. That's by choice. I stop at the linear order. And you see that at the linear order, each Fourier mode is independent. So sometimes these are called the generalized susceptibilities, because it tells you if I try to excite my system at a frequency omega or with a wave vector q, it tells you how the system will respond to such an excitation and tell you how the operator A will grow or not grow, will be big or not big, depending on the perturbation you've applied here. So these are usually called generalized susceptibilities. Now, the thing which is remarkable is that there is a very simple way to compute these coefficients that I will not do, but I will give you the formula, which is simply by expanding the formula, giving the time dependence of the density matrix. So let me give you the formula. So chi of x1 minus x2, t1 minus t2. This is minus I, the complex number, theta of t1 minus t2. This is the Heaviside function. That's the function which is 0 if this is negative, and which is 1 if this is positive, times the average of the commutator of a hat at x1 and t1, and I will explain what this is, O hat at x2 and t2, commutator, and this average is computed only, go away, come on, is computed only with the Hamiltonian H0. So this is an average which is computed only with the unperturbed Hamiltonian, so when you are in equilibrium. And these objects are the Heisenberg representation of the operators. So this is what I call A hat is exponential of I H0t. So A hat of t is times A exponential of minus I H0t. So you see that if you know H0, if you know the operator A and the operator O, you can, in general, compute these susceptibilities. And that's a remarkable formula, which is known under the name of fluctuation dissipation theorem. I don't like the name, but this is the way it is. And this theorem says that if you have a system which is in thermal equilibrium, then the response of the system to a perturbation perturbation is equivalent to the knowledge of the fluctuations of certain observables in equilibrium. You see, this is the ultimate weapon. You deal with an out-of-equilibrium system, which is usually super complicated. You break symmetry of translation. You break symmetry of rotation. You break invariance by this and invariance by that. But at linear level, you can compute the response of the system to these perturbations simply by knowing how certain observables, here A and O, this is what you want to measure, this is what is creating the perturbation, are correlated in the system at equilibrium, which is usually much simpler to compute because here you have the equilibrium Hamiltonian, which means you can benefit from all the symmetries, all the properties that this equilibrium Hamiltonian has. So this is, of course, an extremely powerful theorem or relations. And this is something you can apply to any quantity that you want to measure. And I'll stop here, but I will just ask you one thing. If I want to do conductivity, what will be the operator A and the operator O? So I let you as an exercise. Of course, we'll do it tomorrow. But think about it. I want to measure the conductivity. So what should I take as operator A and operator O in this formula to do it? I give you a second exercise. For tomorrow, which is I put a perturbation which is time dependent. So potentially the energy of my system is fluctuating and is changing. And I ask you to show that the average of the time derivative of the energy of the system as a function of time, so I will put it that way, is simply minus 2 omega imaginary part of the susceptibility O dagger. So if I apply a perturbation which is sum over dx, sum over dx times lambda, I need something which is Hermitian. So sum over dx, lambda of x and t times O plus lambda star of x and t O dagger. This is my perturbation. And I let you do as an exercise that this changes the energy of the system in average. Let's imagine lambda is sinusoidal. So you can think of it as a single Fourier component at frequency omega, that this will change the energy of the system by this formula. And of course, this is computed at the frequency omega. This is much more difficult exercise. So just think about it. Don't worry too much if you have problems doing it, but think about it. Think what it means. That's why it's called the theorem of fluctuation dissipation, because this is what gives the dissipation. But I think it should be called theorem of fluctuation response rather than dissipation, because it gives the response of the system. Voilà, let's stop here. I think it's time for questions. Tomorrow we'll continue by specializing this fluctuation dissipation theorem to the conductivity, see what it gives us, see that we can compute the conductivity of 3 particles, for example, which is already not bad, and then we'll complicate it. And then we'll see that, the situation of our 2 reservoirs and whatever is not easy to describe in this language. So we'll move to the other formalism, which is the Landauer-Büttiker formula, and we'll see how it explains or not the quantization of the conductance that we have observed. Voilà, so let's stop now, and I take any questions that you might have. If you have questions, of course.
So just to recap this,
Yes?
perturbation of X is just the perturbation over space for this exercise?
So O is potentially a function of X, sorry. So I'm just saying, imagine, for example, you apply a perturbation which is chemical potential, change of chemical potential. The lambda will be the chemical potential, and O will be the density at point X. Now I could imagine I apply a chemical potential which is spatially varying, and but let's ignore the spatial variations and just look at the time variation. So let's imagine lambda is cosine omega t. Just you apply, and then of course then this average will be over one period of the thing, because of course the energy will also oscillate with time. By the way, the energy is what I call E of t. This is of course this is the trace of the density matrix of the system at time t times the full Hamiltonian of the system at time t. That's the average of the energy. So this one contains the perturbation as well. This contains the perturbation, and then you have to play with the two to get it. Voilà. Today we saw quite general things, so I guess maybe the questions will come more after we've seen a little bit more with this. Or, but yes?
Might be a very strange question, but those two operators, A and theta, or O as you call it, for every A is so unique? Or,
No. I can, for example, say, let me put a perturbation which is, I change the chemical potential. Then O is the density. Now, I could say, let me measure how the density is changed. In which case, A is also the density. But I could also ask myself, if I change the chemical potential, do I induce a current in the system? In which case, A will be the current. I have no reason. I can choose whatever I want depending on what information I want on my system. Nothing prevents you from putting a magnetic field and asking what is the current which exists in the system. Or you can ask what is the magnetization of the system. So there are pairs which are more natural than others, but technically nothing. You can insert here any operator depending, and here, depending on your perturbation, you have a given operator which is fixed. If you put a magnetic field, this will be the magnetization of the system here, and there you have no choice. But then you can measure the magnetization, you can measure the current, you can measure the change in density, you can measure whatever you want. Many situations will immediately give you zero. Je veux dire, if you change the chemical potential naively, you would say, oh, what is the magnetization? Well, I respect the symmetry up equal down, so magnetization will stay zero. But you can check it explicitly if you want here. So you can choose A as you want. There is no limitation, absolutely no limitation. That could be also a cool exercise. Play with changing the chemical potential in a system and check that, for example, you would get no magnetization in the system. Are there other questions? Yes?
Sorry, was this the Kubo formula?
No. So the Kubo formula is this specialized to measuring the conductivity. So this is, if you want, the most general formula one can write. The Kubo formula has two little things. You could say, oh, now it's trivial. Why did Kubo get famous? Because this was known before. As you will see, there is a little glitch that if you just do this, you get it wrong. So he got it right. And then, of course, there are the consequences when we'll use for the Kubo formula. There is a little glitch also for the conductivity because people who invented conductivity were naive and didn't know what a gauge potential was. And stupidly, they defined the conductivity by the connection between the current and the electric field. Unfortunately, if you think about the perturbation that will appear in your Hamiltonian, it's not the electric field that appears. So there are twitch in the conductivity that you have to correct compared to this formula because of that, actually. And then there is another one we will see tomorrow, which is a little bit more complicated. But the Kubo formula is exactly this formula, but with a proper insertion of operator A and O for the conductivity, and the proper modifications to take into account the little twitch that I'm mentioning. Are there other questions? No? Well, then let's call it a day. Think about the exercise. So tomorrow, I'm expecting all the exercise to be done, of course. No. So we will of course discuss that. No, but try to think about them. I think it's fun, and certainly the one on the Kubo formula. Don't hesitate to do, because it's relatively easy to identify what is the perturbation and what is the operator A. What is the operator A? You want to measure the current. So A is the current. Okay, now you just have to identify O, which is the perturbation, and then we'll see. Okay, let's stop here, and we continue tomorrow.